Good day viewers. On the EEVBlog there's a couple of threads going back about 8 years now, running in parallel, about designing a Picoammeter. And very early in the piece, one forum member going by the name of Gyro presented his design for a Picoammeter adapter. It was just a photo of a hand-drawn schematic. A number of people made it and reported that it worked very well. So I thought I'd do it as well, and this is it. Now, why do I want a Picoammeter? Yeah, I've become interested recently in high value resistances and therefore very small currents, so Picoammeter is what you need to measure them. Now I'll just show you the design for this thing, and then the construction of this, and then we'll do a few experiments. So there's the schematic. Input here, output on a couple of terminals. There's the input, a ground connection, and the output terminals. And this is the guts of the amplifier. So it's a transimpedance amplifier. It means it converts current into voltage. So that's the essence of it there. This here is a bit of output protection, and this business up here is for generating a virtual ground from the 9-volt battery, and an offset adjustment for correcting offset errors in the op amp. They're both in the same, it's a dual op amp, so that they're just two halves of it. It's an LMC 662, which features extremely low input bias current of a couple of femtoamps, which is what you need for something like this. So here's the classic transimpedance amplifier. It consists of just one resistor, and the gain, or transimpedance, which is volts output per current input, so volts divided by amps, which is ohms, so the transimpedance is measured in ohms. That value of the gain, the transimpedance, is given solely by one component, the feedback resistor, which in the case of this circuit is R2, which is 1 gigohm. So it has a transimpedance of 1 billion. This other resistor here is not shown there, and it doesn't really have any effect because both sides of it are at virtual ground potential, so there's no voltage across it, therefore no current through it, but it does help in protecting the inputs to this op amp. Up here we have the battery goes through a switch to the plus and minus rails. This voltage divider picks out exactly the midpoint, so this op amp, through a very low impedance connection to ground, makes this ground point at 4.5 volts either side of the rails. It's sort of like the tail wagging the dog. This is held at ground, and the op amp adjusts it so that that is exactly 4.5 volts above this point, and this is 4.5 volts below. So it swings the rails either side of that ground to get it exactly centered around ground. And we've got a trim pot here that selects a fraction of that voltage centered around the midpoint to make small adjustments in the offset voltage to get zero output when there's no input. So this gain of 1 billion means for every amp that you stick input there, you'll get 1 billion volts out, which is clearly ridiculous. So when we temper that with reality, we see that the op amp has just this 4.5 volt rails to work with. So the most voltage you can get out is 4.5 volts, which corresponds to an input current of 4.5 nanoamps. How much current can you stick into this? Well, looking here, the input current doesn't go into the op amp because op amps typically draw negligible input current, and in the case of this thing it's only a couple of femtoamps, so all the input current has to be sucked out through that feedback resistor, which the op amp does by pulling the output in the opposite direction to the current, so that when that's positive current, this output is pulled negative, and that makes the current flow out through the feedback resistor. Now the maximum current that can do, of course, is the maximum voltage divided by that resistance. 4.5 volts divided by a gigohm means the most current it can force out that way is 4.5 nanoamps. After that, these 2 points here on the input to the op amp are no longer held equal by the op amp action, and the voltage will start to increase. And that's why that resistor is there, so that voltage is absorbed through the resistors and shunted by the input protection diodes of the op amp. Now that's a megohm, so in theory, since these input protection diodes can handle 5 milliamps, in theory you could put 5 kilovolts in there before they saturate and burn out. So even though this thing works with tiny currents, which you only need small voltages to generate, you can still stick in something like 4 kilovolts, which I find quite amazing. I'm not going to try it. Now this is my kit of parts for a Picoammeter that I want to make. It was a design by Gyro in the EEVBlog. I'll put a link to the thread in the doobly-doo down below, which produces 1 millivolt per picoamp. So you run your picoamps through here and out comes millivolts there. Why do I want one? I just do, alright? I have been a bit fascinated with high resistances lately, and I'd like to explore properties of insulating materials even at high voltages. For instance, these standoffs here are Teflon, and even they may be a bit sus to use in this thing. You see the terminal coming out of that chip, that's the input, and all this stuff is going to be hanging up in the air, and maybe even these standoffs holding that up shouldn't be there. Maybe all this should be up in the air, but we'll find out. But yeah, even Teflon, which is an excellent insulator, 10 to the 14 ohms per something or other, which is higher than pretty much any other material, it may not be good enough. But that's the sort of thing you can explore with a meter like this. And I've got a 4,000 volt power supply, so I can output precise voltages and hopefully measure precise very low currents and work out what sort of resistances I'm dealing with. It'll also be interesting to explore things like reverse leakage current of diodes and transistors, protection diodes, gas discharge tubes, a few things, but basically just for fun. So, and if we look at the board, I can touch this because it's low impedance-ish. An LMC622, which is a op amp or dual op amp with extremely low bias current in the order of femtoamps. There's a few parts on the bottom, but there's not much to it. There's a gigohm or 1 gigohm resistor there, some other resistors there to make a 1 megohm resistor on the input. So that's between the input and any of the rest of the circuit. So you can probably stick 1,000 volts in here and it won't care, which seems a bit odd when you're talking about minute currents that you can stick 1,000 volts in, and that's a compensation capacitor part of the op amp circuit. Yeah, so let's stick this thing together. With the label stuck on, I could drill the holes for the terminals and the switch. Now, these terminals are okay on a plastic box, but in a metal box there's nothing stopping them short against the metal, so I had to put nylon washers on them and then much bigger holes to hold the nylon washers, and then the washers stop it rocking around, and still got to wire it up. And there's the battery bracket in the case, standoffs for the board and foots, and the battery case. There's some foam on there to give a bit of pressure. And it fits in very snugly. So, come along well. Next thing to do is wire that up and put the circuit board in. Okay, connections, ground and the input terminals, and wiring done there. Teflon standoffs and brass one done. Just got to screw that on now. I'll mount this first, then put that on. Right, all that intermediate construction stuff was filmed a few months ago, but back to the present. Here's the finished thing. Take the lids loose, take it off. This connector unplugs, so we've got the power switch and the output terminals separate. And in here we've got, there's the op amp. Most pins go into the PCB, but the high impedance node is a flying lead going up to here, which is this terminal. Those two terminals are both on Teflon standoffs. So the input here, the 1 meg resistor consisting of 4 249k resistors is between those two terminals. There's the 1 gig feedback, and the other standoff is brass, that's the output. There's the trim pot or the offset trim adjustment, the battery pack just fits in nice and snugly there. 6 1.5 volt AA batteries, gives 9 volts. A couple other things I should mention, because the way this works by pulling the output in the opposite direction to the input current, it's an inverting amplifier, which is why this is the minus and that's the plus, when you'd expect the plus to be, you'd expect the groundish one to be the minus, but they're reversed. And you see here I've got the red going to the black because I really should have swapped them in that connector and had black going to black, but I've got hot melt glue on it and it's too late, so I have to swap them here. Also, that input B and C connector is a high voltage type with a longer insulation there, so I don't know if it really matters for this. Presumably that's Teflon too, so yeah. Alright, let's do some experiments. Right, here I've got a 1 gig ohm resistor just like the one inside the unit, and measuring it. It's almost at the limit of what this meter can measure, but it's a bit over a gig. It's 1176 meg ohms, so very high. Now, to get even 1 milliamp to run through that resistor, you'd have to stick 1,000,000 volts across it. That's how high a resistance it is. Now, obviously there's extreme practical problems with trying to put 1,000,000 volts through that, but you can stick 1,000. It's rated for, I think, 8 kV, so let's just stick 1,000 and you should be able to see a 1 microamp deflection on this. Right, power on, 999.9 volts, 1,000 volt range, and it's in standby, so I hope that's visible on the camera. Should see that's 50 microamps full scale, so 1 microamp, which is 1,000 volts into 1 gig ohm, should give just 1 microamp, just the smallest one division of deflection down there. So turning it on, there it goes. Negative, it should go 2 steps the other way. Yep, and off, back to 0. So yeah, 1 microamp. Let's do that using this guy and 1,000th the voltage and then 1,000,000th the voltage. Right, here we've got the DC voltage source set to 1 volt going into the adapter, ground to the case, and voltage going through that 1 gig resistor to the input of the meter. And we're looking at its output up here. And first we turn this on. I've got rubbish, so turn it on. Okay, very low value, but it does wobble around a lot, especially the bottom 3 digits, and I'm not sure why that is. So I think there might still be something wrong in here. I'll show you a bit more on that later, but yeah, let's call that less than 0.1 of a millivolt, which is less than 0.1 of a picoamp. So turning on the output from here now, and we get 1 volt out. 1 volt through 1 gig is 1 nanoamp, and this produces millivolts per picoamp or volts per nanoamp. So we get 1 volt meaning 1 nanoamp. Now, if we go bump this up to 2 volts, we get twice as many nanoamps. 3, 4, 5. We've pegged the meter. It's at 4.5 volts, which is the most that this thing can put out. So 4.5 nanoamps is the highest we can get. If we go above that, sticking 5 nanoamps through it, we peg the meter. So back down to 1. make it 0, and we're down to again that 0.1 of a picoamp-ish, and go down here to the millivolt range. 1 millivolt through a gig ohm should produce 1 picoamp. So turning on the output now, and we're getting about 1 millivolt up there, which means 1 picoamp flowing through here. Again, if we bump the voltage up, 2 picoamps, 3, 4, 5, 6, 7, 8. So it seems to be tracking the picoamps pretty well. We've certainly got picoamp resolution. If we go back down to 1, and now just bump up the voltage by 100 microvolts, which corresponds to 100 femtoamps, we should see that 0.1 go up to 0.2. Oh, we've got sensitive to me being near it. So we've got 1.0 noise. Bump this up to 1. 1.1 noise. 2 noise, 1.2 noise, and so on. Up to 1.9. So its resolution, if we call that noise and everything above useful, then that digit there is 100 femtoamps. So that looks like the resolution of this thing, which is pretty damn good, isn't it? If we turn this digit off, well, let's clear it, and just put a 1 in there. No, not there. Now we're sticking 100 femtoamps through it. Yeah. Cute, eh? Measuring picoamps with roughly 100 femtoamp accuracy. Pretty impressed with that. Oh, and by the way, if I bring that node out, have any sort of wires running up here, the noise gets out of control. And so really this thing should be in some sort of a shielded enclosure, and I've tried bringing this down right over all that, so it's pretty well shielded in there, and it doesn't have much effect. There is this noise which is coming from in here, and I don't like it. Maybe it's oscillating crazy or something. But despite that, we still seem to be able to get 100 femtoamp resolution. What else can we do? I was going to do I did try some experiments with trying to stick higher voltages through this piece of high density polyethylene and measure the current coming out of it, and it was all pretty inconclusive, and it became quite obvious that noise is a big issue. So this I need to come up with some sort of a shielding contraption to put all this in. But just looking back what we were doing before, 1 millivolt going through 1 gig producing 1 picoamp, which this represents as 1 millivolt coming out. There we are again, and it works. We put double the millivolts in, we double the millivolts out, and so on. Put 5 of them in, get 5. But if we look at what's coming out of this thing on the oscilloscope, we see this bloody mess. It's super noisy. That's on 50 millivolts per division. If we go down to 2, which is the sort of measurements we're trying to make here, it's just hopeless. There's all sorts of junk down it. It's just horrible, and it's not coming from this. If I turn this off, it doesn't really change. So it's not oscillations inside the adapter. In fact, if I just unplug that from the adapter, okay, that reduced it a bit. So it's picking up crap from somewhere. So I think I need to do a serious look at shielding and grounding and stuff. Yeah, so this works, but there's a lot of noise on top of it. Makes me wonder if maybe inside here there should be another amplifier after that boosts it out of the noise, maybe 1,000 times amplifier on the back of it, or 100, and then higher voltage rails and or range switching using different values for the feedback resistor. Stuff to play with, but the thing works. It's just that its output, at least the way I've done it, has got a lot of noise in it. So if I find something that improves things significantly, I'll post a follow-up. But for the moment, we've got something there. I'm pretty happy with it, as long as you don't look at it on an oscilloscope. Just look at it on the meter. Further experimentation required. Hope you found that interesting and confusing like I did, and catch you later.